Hello, everyone. Let us start. Now, I just want to make sure if these students are absent. Number 6, number 9, number 10, number 11, 14, 15, 16, 17, 20, 22, 24, 25, 26, 31. If you're here, please let me know. Okay. Now, first, let's look at the homework. We have 2 assignments. Assignment number 3, limit at infinity. Now, in this exercise, I want you to know just some certain points to be aware. 11. Now, in this answer, I divide x cubed. Now, during the lesson, I said divide x squared. Now, in this question, it doesn't matter. Whichever one you choose to divide, it will work. Now, let's say we're dividing x cubed, and then you get this. You get this. When you get this, do not write anything like 3 plus 0 and then 0 plus 0 plus 0. You are not allowed to write that because that's undefined. You are not allowed to write anything that's undefined. Okay? What you should do is to discuss what the denominator and the numerator would be when x tends to infinity. So you should discuss when x tends to infinity, the numerator, that's one part, and denominator at the same time. Some of you just mentioned the denominator. Some of you just mentioned the numerator. It's not enough. You mention both, okay? And then you say, oh, this result, this sentence, you said the whole sentence. You say, oh, the result increases indefinitely when x tends to infinity. And then you say the limit does not exist. I hope you learn. This is how you should write it. Another problem is question 17. During the lesson, I said you should not expand. And again, you should not expand. Please look at the answer and see how you can get the final answer without expanding. You see, without expanding. And the last question you did quite well. It's just here, some of you made a careless mistake. When you divide x, in the radical sign, you are dividing x squared. So there it's x squared. Okay, that's assignment number 3. Assignment number 4. Now this one, not huge problem. It's just something I do not allow. For example, I do not allow you do the simplification of fraction like this. Okay, I do not allow that. Although you may think, oh, I will divide x and divide sine x. You're not allowed to do that. Okay. And also, when you are evaluating, in my opinion, you are evaluating, trying to figure out what the limit is. Now, you should know that when you take limit, you take limit to every part of that function. You do not just take limit of some of the parts. What do I mean by that? Now, because let's take a question 4, for example. Now, in the other questions, you may do the same thing. That is, when some students, they realize, oh, this limit is 1, they will try to simplify it by not writing the first part. For example, they will not write this. They think, oh, maybe this is too much to write, only because the writing costs too much time. And then they decide to write this because they know the first limit is 1. So they choose not to write the first part and only write the second part. And the first part, they say, oh, this is equal to 1 already. If you read the textbook, you will find that never exists. That never appeared in the textbook. And in the standard answer, that's not also never would appear. Would not never appear. Technical sense, that if you want to say, oh, the value of one part of the function is equal to 1, let's say 1 or 0 or whatever value you think it is, you think that part, the value is found, you are not allowed just to take that value and ignore the rest of the function. That is not allowed. In other words, you're not allowed to find a certain part of the limit. You are only allowed to find all the limits at once, or at the same time. If you read the answer to all the questions, you will see the same pattern. You see, now when I have every part, you see I have 4 parts, right? In this function, I have 4 different parts, and then I will have limit 1, limit 2, limit 3, limit 4. I will only the coefficient can be taken out. That's allowed. Now, let's say 3 parts. Now I will send the limit to the 3 parts at the same time, and then in the next step, I will get the limit of each part at the same time. I know it sounds crazy. Oh, why can't I just find one part step by step? Isn't that easier for me? I know that's easier for you. I know. I understand. But technically, you're not allowed to do that. You're supposed to find all the limits all at once. Otherwise, you're not allowed to find any limits. Now, I'm willing to discuss this with you after the lesson. It takes a while to understand the true notion behind it. Why can't we just find one and then write it simpler and simpler and simpler? It's not okay. All I can say is you try not to do that then. Not saying, oh, in the exam, will you be marked down? I think that in the exam, in the public exam, is that our question won't be as hard as these exercise. Now, technically, because we have observed so many years now, we see that the limits part, the exam questions are not that hard. So in the public exam, we never had this issue. Okay, we never had this issue because you won't be dealing with a lot of parts. But should it be allowed that you find one part of the limit and then the other parts? So we don't know how they mark it, but technically, if you read through all the textbooks and all the answers, they never do that. And I know the reason why. I do know why they don't do that, because it's not good. It's not good habit. But I'm willing to discuss with you later after the lesson if you're interested. Now, because there may be some possible mistakes if you do that. Okay, that's it. That's it. Now, some of you get A-, maybe because of that. Maybe because in your presentation you did that, and that's not ideal. Okay, and I didn't ask you to redo, because if I ask you to redo, I don't know if you know not to do that. So I will just speak in front of the whole class, and later on you can try to avoid it if you can. Okay, that's all for the homework. Now the lesson. Now, girls, this is the last, how do I say? This is the last, sorry. This is the last special limit. Now, if you ask me what type is it, I should tell you this though. This limit, although we study it in the last part of the chapter, but this limit, if you want to discuss the type of it, it's still the first type. Meaning, I'm just in this function, there is a small little thing that is discontinuous, and I can factorize so the discontinuous part can go away. But why do we study this one this late? Is this because the type of this function is quite difficult? It's even more difficult than trigonometry. Okay, and that is the exponential and log. Okay, the type of this function is exponential and log. Now, if you think about it, it's even harder to factorize exponential or log. It for trigonometry it's almost impossible, but we found sine x over x. But right now we need to find something else for exponential and log. So the first lesson, before we do all that, we have to go through this special limit. And this is not easy. This is not easy. In this lesson, we need to understand there is a number e that is naturally there, and we need to study it and understand and know its value. Okay. Now, first, let's consider a function like this. This function has a depending variable y and two independent variable a and b. Now, of course, the value of y depends on the values of a and values of b, right? And we need to examine its behavior. What behavior? The value of y, the behavior of the values of y when a and b increases separately, when a increases or and b increases, and see what y would do. And we have two columns, the table to fill in. Now, suppose b is fixed. Now, I will just fix as b equals 3. You can fix b equal anything as long as it's a fixed value. It will not matter. Now, let's say b equals to 3. And then you can see I increase the value of a gradually from 1 to 10 to 100 to 10,000, a million. And that I will use my calculator to get a few values. Okay. For the first one, I will get 8. That's 2 to the power 3. I get 8. For the second one, I will get 1.1 to the power 3. That's 1.331. And next one, I will get 1.01 to the power 3. It's 1.030301. And next one, I get 1.0001 to the power 3. I get 1.0030003 and something, I don't know, because my calculator only provide 10 sig figs, 10 sig figs. I suddenly forgot about the name. Now, for the next one, when a is 1 million, then it's 1.0000001 to the power 3. It's 1.0000003. Okay. Now, if you see the pattern at the beginning, it's 8, and then it becomes smaller and smaller, right? And I will ask you to guess now what the limit is if A increases indefinitely. And like I said, the whole lesson, the whole chapter is based on your ability to guess. And your guess should be 0, should be 1. This should be 1. Okay. Is that okay? Because we can see basically it's this. Now, if B is fixed, then the limit of A tends to infinity of 1 plus 1 over A to the power B is equal to 1 plus, is Anna here? 1 plus limit A tends to infinity 1 over A to the power B. Then it's equal to 1 plus 0 to power B. And then it's equal to 1, basically. Now, if B is fixed, and when A increases indefinitely, you will get that. Now, the second column, I'm going to fix A. Let's say A equals to 1. And then I'm going to increase B slowly. When B equal 1, 10, 100, 10,000, and 1 million. And let's see Y, the behavior of Y. For the first one, the value of Y is equal to 2 to the power 1, that's 2. The second is 2 to the power 10, that is this. Next one is 2 to the power 100. I don't know how to calculate this one. And the next one is 2 to the power 10,000. And the next one is 2 to the power 1 million. As you can see, if A is fixed, then I increase the value of B, then the value of Y will get to infinity. Or you say it does not exist. Does not exist. Okay. Now you can see that if the two variable A and B, if they increase one and fix the other one, I think they will have opposite effect on Y, where A will bring Y to smaller and then B will bring Y to bigger values. Now, the problem is, what if I send A and B to infinity at the same time? It's like a battle between A and B. At once, on one side, A is bringing Y down, and then on the other side, B is bringing Y to increase indefinitely. But which one would win? So the next activity is to find out which one, A or B, would win the battle. Is that, with this value, with Y tends to 1 or Y tends to infinity, which one is it? And we have a third experiment, the third trial. Now, when A and B equal 1 at the same time, A and B equal 10 at the same time, A and B equal to 1,000 at the same time, A and B equal to million at the same time. And we can do this experiment. So the first one, it's 1, 2, it's 2. 2. For the second one is 1.1 to the power 10. It's 2.59374246. Third one is 1.001 to the power 1,000. It's 2.716923932. And then the last one is 1.000001 to the power million. That is 2.718280469. You see? Now, I think 1 million is a pretty large value. It does reveal something because you see when A is 1 million, this value already is very close to the limit. And when B is 1 million, this value also is quite large that my calculator can't even express this value. Okay. Now, so I think that when A and B are both 1 million, maybe this value is very close to the limit. Agree? It's big enough. I mean, A and B is big enough. But you can see that Y does not tend to 1 or to infinity. It is balanced. I mean, it's like A and B it's a tie that neither of them wins. That they strike at a balance at 2.7 or something. And this is a very strange phenomenon that it's either A or B. The value is equal to 2.7 something. And this value is what we call E, the natural number, And we know that this value is a non-terminating, non-recurring decimal. It's very similar to the value pi. And how do you get it? You get it by increasing A and B at the same time, at the same rate. Okay, and that's what you learn. That's what you learn. That's how you get E naturally. How do you get E? You take this, you don't write A and B anymore, you write N, and A equal N, B equal N at the same time, and you send N to infinity. That this is equal to E. Okay. Now, if this is equal to E, this is also equal to E. That's 4.8B. Now, when T tends to 0, that's like 1 over N. T equal 1 over N. And the power is 1 over N. You know what I mean? Like if you replace N with 1 over, if you would replace 1 over N with T, then you get the same limit. That's also equal to E, but this time is T tends to 0. The value is E. This one is when N tends to infinity. The value is E. Is that okay? Now these two you have to remember. Otherwise, okay. These two you have to remember. Otherwise, I don't know where else can you get E. But you can think about these ones. Now, if I change this a little bit, are they still equal to E, right? I would say you should not answer too soon. With this, if I change this a little bit, I think these two, after the teacher's instruction, you should realize they are at the same limit. But what if I change this, but I send N to the negative infinity, is it still equal to E? You should not speak too soon, right? You should not. And this one, I changed the sign. Basically, I changed the function, right? Is it still equal to E? You need to verify. You need to verify. And after verifying, you can use it. Okay? If it's equal to E, then in the future, you can use it if you can remember. But if it's not equal to E, you should also accept that. I don't think it will always equal to E if you change the function to entirely another function. It's not always. It's not always. Later on in this lesson, we're going to evaluate a lot of things that look very similar, but not exactly the same. Okay? Note, E is an irrational number. It's non-terminating, non-recurring decimal. How do you get E from the calculator? It's shift something. Where is it? Is it shift IN? Yes. I get Shift IN, it's next to log. Shift IN, that's e to the power, and then you put e to the power 1, and then you get e, I think. 2 point, I think the first 10 digits are 2.718281828. Okay, it's not recurring though. It's not. Definition. Now after, this is after e. You know that e is a value. Okay, e is a value. Now this one is a new thing. This is not e. This thing is e to the power x. Okay, this thing is e to the power x. And it's an exponential function, but you use the base as, you don't say write 2 to the power x, you write e to the power x. Okay, and look at the definition. I think on the left-hand side, it's easy to understand. It's just base e and then x. What is e squared? Then you use e times e. It's easy to understand. Left-hand side, e squared equal e times e. E to the cube, e to the power 0.5. That is square root e, basically. Left-hand side is e to the power x. Right-hand side is equal to a limit, and the limit has n in it. Now I need to explain why this is so. Why this is so. This is so because of the right-hand side. The right-hand side. This is so because some limits property. That is so. Okay, I will prove it to you. It's very easy to prove if you know the limit property. Because the right-hand side, and this is the right-hand side. It's equal to limit n infinity. Now, I will write this to as n divided by x. Okay? Don't blink. And then I'll rewrite this. And then this is nx. Is it fine? And then you will see I will do the limit. Okay. And here I will change it a little bit. I will change n tends to infinity to n over x tends to infinity. And then I will get e to the power x. One moment, please. One moment. Okay, I'm back. Sorry, I still don't feel very well. Let's continue. Let's continue. Maybe it's a good thing that we had to stop for a while, but you can see that the right-hand side turned out to be e to the power x in the end. But in the middle, I use the limit of a power is the power of limit. I use the property of limit. Now, you may ask me, oh, Ms. Chen, why do I need to study that? Indeed, if you are exam orientated, then you don't have to really study the right-hand side. You know the left-hand side, that's enough. You know what's e squared, right? You know what's e to the power 3, e cubed, and then that's fine. Why do you have to study the left or the right-hand side? The implication of the right-hand side is very deep. The meaning of it is very deep. This is because, I don't know if you realize, this part you can completely ignore, but I don't know if you realize that you have never studied. I mean, you have never, I think that as your teacher, I have never taught you how you multiply pi to pi. Because like, if you say, oh, this is pi, this is another pi, these are, what do you say? Non-terminating, non-recurring decimal, right? Now, if you multiply, you will not know how to multiply that because they have infinitely many digits. So technically, the definition of irrational numbers are not well defined yet for you. Okay. So that is why the right-hand side is put there. So you know what do you mean by what e square, right? What do you mean by e square? What is e times e, right? What is e and then take a square root? What does that mean? I think the right-hand side gives you a definition of e to the power x. Okay. It is not the same as, oh, what is 2 squared? 2 is 2 times 2. And you know what's 2 times 2? 2 times 2 is 4, but you don't know what e times e is. So this is what it is. Anyway, if you don't want to look into that, that's fine. But this proof I wrote here in the margin on the right-hand side can also provide an exercise, because later on you will do some exercise to verify some limits that is very close to e but not e. Okay, now the e to the power x, this is the function. Okay, this is function. You should just treat this function as any other exponential function. What do I mean? I mean e2 to the power x. I mean 3 to the power x. You see the graph is very similar. Now this is increasing because e is greater than 1. So you can only see increasing, you don't see decreasing because e is not between 1 and 0. So you see this graph, it also passes through 0 and 1. The y-intercept is 1. And on the left-hand side, it's going to asymptotic to 0. Asymptotic to 0. That means when x tends to negative infinity, e to the power x, the limit is 0. Okay, that's what I wrote. Okay. Now the first note, you should just accept because it's true for every other exponential function, because the graph is continuous and the function is defined for every x. That means the domain of this function is all real numbers. There is nothing that e cannot get power. The power e can you can write x as anything, e to the power 0, e to the power negative value, it's all defined. You may find it weird. I think in the past, I will all find it very weird. But right now you have calculator. You just input and then you get a value, so you don't feel that weird. But in the past, you can imagine that I have a non-terminating, non-recurring decimal, and then the power of it is just very, very, for me, it was very puzzling. Okay, but you now know that it's all defined. It's all defined, like every other exponential function. The property. Now, this property, I would ask you to, what do I say? If you can memorize it, okay? And remember it as you can just write it. Now, but you may say, oh, this is too hard for me. How do I know they're equal, whatever? Now, this is this, okay? This is this. First of all, the right-hand side, the pattern is very clear. The first one is, you can say this can be x0 over 0 factorial. This can be x1 over 1 factorial. The pattern is easy. And if you want to, you really can memorize it in one day. But the meaning behind it, because this is not included in our curriculum, so I just put it there, and then maybe you can use it, maybe you can't use it, I don't know. Now, this right-hand side can be seen as a polynomial that can be approximately equal to e to the power x. Now, if you think about the meaning behind this equation, you will see that on the left, you have an exponential function, but on the right-hand side, you have a polynomial. Okay, although they are not completely equal because there are a lot of terms. Here you have infinitely terms. You can still write the next term and the next term and the next term, but you can see as they are approximately equal, meaning that if you want, you can write as many as you want until you find, oh, they are almost to your liking, like, oh, I have got enough, then I don't have to write anymore. So this is very profound if you think about it. And this provides later on you will see that in this whole section of this chapter, we want to use this as much as possible because this is how we factorize things. Now, if I have an exponential function, I can never factorize. I must change it to polynomial, and then I can factorize. You know what I mean? So this is the way to really change exponential function to a polynomial, although not exactly equal to, but close enough. Now, the next one, the second equation is just take x to 1. You just substitute when x equals to 1. And then this can be seen as an approximation of e itself. Like e equals to, this is 2 point something, right? These are the decimals, you see? These two, 1 plus 1, are the integral part. And these are the decimals. You can write as many as possible until you think, oh, I get pretty close. I get close enough. Is that okay? Now, when do we use these property? Only a few times. Only a few times. I will mention them when we use them. Okay, that's all. That's all. The first page is it's quite hard. It's quite hard. From the original function, and then you know the existence of this value, and then you know the limit is equal to e, and then this limit is equal to e, and then the function using e as a base, and then something else about e, and something else about e. It's all new. It's all new. Do you have any questions about this part? Now, to new students, I would say though that just consider this as another irrational number, a rather important irrational number. If no question, let's move on. Move on. Now, starting from the next page, we're getting the easier part again. This part we will just have a revision. Basically, what are the rules for the indices? It's the same rule. You have additional law, the subtraction law, this law. It's all the same. The zero index and the negative index and the fractional index. They're all the same. Okay, although the base is irrational. Okay, I think you're fine with that. The next one is the natural logarithms. The natural means the log to the base e. Okay, and let's study log again. Let's study log again. Just as I just assume that you don't know log at all, so I study log again. The first equation is exponential equation when m equal e to the power n. And then if you write another equation, which is in terms of m, and the subject is m, the power, you must write ln, which means log to the base e n. Okay. Now, please note that in this definition, m cannot be negative or zero. If m is negative or zero, then log m is undefined. It's the same as other logs. Number two, conversely, if n equal, you can write it backwards. Now, if n equal log m, then m equal e to the power n. Okay, and then this is the log function. The log function looks very much like any other log function. I think the curve is just a little bit different. And you can see that a log to the base 2 may be a little bit higher because this one is higher. This base is larger than 2. So log 2 will be higher, but log 3 will be lower. You know what I mean? Because this one is 2.7 something. This one must be 2 and this one must be 3. I think. Yeah, but they have similar curve. Okay. Let me erase it. Now, I think you should answer this question because we just studied graphs, right? We just study graphs. Now, let me change this a little bit. It's not log y, it's y. Change this a little bit. How do you fill in the blanks? Basically, when is y greater than 0? Basically, you're solving y is greater than 0. When is y greater than 0? Now, I will ask a student and you must answer immediately. Emily Cole.
When x is greater than 1, then y is larger than 0.
Very good. Yes, you must highlight greater than 0 and then answer the range. Okay. Now the second one must be easier. May, can you answer this one? I think May may have some problem on the connecting problem. How about Cassandra? Can you answer, Cassandra?
When x is smaller than 1.
Can you think again? Because there might be a better answer.
X is larger than 0, but smaller than 1.
Yes, correct. Okay, so that is I didn't know there is a question like this. It's very timely. Huh? So second note, the function is continuous for all values of x. For all values of x. No, not for all values. For all x greater than 0. Not all values of x. Okay, sorry, I made a mistake. No, it's continuous when x is greater than 0. When x is smaller or equal to 0, there is no value. So you cannot say continuous or discontinuous. Okay. 3. When x tends to infinity, log x also tends to infinity. The limit does not exist. Okay. Now, when I write limit equal to positive infinity, doesn't mean the limit is equal to a value. Okay, that means it does not exist. Properties of log. Now, these are the property of any log, but also the natural logs. You see, this one you use all the time. This one you also use all the time. But I don't know if you use this all the time. ln, not log, ln 1 over n equal negative ln n. I don't know if you use this all the time, but this is also true. Okay, now this one you can take out the power and put it in front as a coefficient. Still works. And this one log 1 equals 0 still exists. Log e equal 1 because the base is e. It's like log 10 equal 1. That's common log. Log 10 is common log. Log e is natural log. Now log e is equal to 1. And the last one is the change of base. If you don't like this base, you can change to another base, but I think it's almost always backwards. Usually you need to change other log back to this base in order to apply some of the results that we have here for limits. If it's in other base, you may want this base. This is what I think. Okay. Okay, now evaluate without calculator. This is just some log thing. So this is equal to √2 times log e. That is √2 times 1 equal √2. Okay. This one is equal to this one I really don't know if you know. This one is equal to √3. This one I don't know. There is nothing I can do. In the textbook, you also have this example. And if you look through all the properties you cannot find this property. Right? You cannot find this property. How can you find it? This is because this property is not the property. This counts like as a definition. Is it fine? Because if you see, if you don't realize this, let's say if e to the power log √3 equal t, and then I can take log, right? I can take log, and then I have log e to the power log equal log t. And then I will put log √3 times log e equal log t. And then log e equal 1. You will have log √3 equal log t. And then you realize, oh, t equal √3 immediately. So it's like saying something backwards. I don't know. It's like circular argument or whatever. This is equal to log 3. Maybe you just know another what do I say? Another identity you may not know. That is, do you know a to the power log ax equal x? That you can use it here. Okay. And if you really, really don't know, you can still use calculator to cheat a little bit. In the end, you will find it's equal to 3, okay? This one, this is equal to log e over 2 times 2 over e. This is log 1 equals 0. Classwork. Now, classwork, as usual, you will turn on your cameras, and then when you are done, you raise your hand. Okay. The answer. I asked one student and she should tell us all the answers. A, B, C, all of it. Justina.
For A, it's -1, B is 5, C is 2.
Yes, -1, 5, and 2. Good. Let's continue. Continue. 12 is also, it's just a practice of using the, this time is an equation. When you solve this equation, you can copy the equation. And then you solve it. Just use your knowledge to solve it. In this case, I'm going to solve it like like a quadratic. And then e to the power x minus 5, 12x plus 4 or plus 1. So e to the power x equal 5 or e to the power x equal -1. Now for the negative value, I will say it's undefined. It's not possible. Not possible, not undefined, not possible. Now x can be anything, but e to the power x can only be positive, okay? And this one can x equal log 5. Log to the base e, natural log 5. Classwork, you do it. You tell me the answer when you're done. You need to find the value of x, not just solving the quadratic equation. Okay, Charmaine, can you tell us your answer?
I got log E4 or log E1/2.
Yes. Now, girls, when you express your answer, you cannot write a decimal in M2. This answer is simple enough. Okay, log 1/2 as your answer. Log 4 as your answer. Okay, don't write a decimal. Do not. Hey, this example. This is a simple limit. It's a continuous function. So I will just do this is equal to log limit x equal to 2x squared minus 3x like this. So I'll just put it in. This is 8 minus 6 equal log 2. Okay. This is very simple. This one is also continuous. So I just put it in. Is that okay? 7 e to the power, no, 7 minus e to the power 0. 7 minus 1, 6. Now this is not even like type 1. This is like continuous, so this substitute, okay? So this one is e to the power log 2/3. So 2/3. I think the easiest limit that you can imagine is continuous function. Fix this. If figure out and tell me the answer. Figure out, tell me the answer. Okay, this time I will just show you my answer. You look at my substitution. The first answer is 0. The second answer is -3, not 5. -3. And the last one is √5/5. Next one. Now we're doing type 1 limit. Example 13 is not even type 1. Example 14, starting from this one, is type 1. Okay. And this type 1 is based on, if you still remember, a few minutes, maybe 30 minutes ago, I talked about this exponential function changed to polynomial. Remember that? Now this limit. How do I figure out this limit? Of course, you can do experiment and guess. But there is a quicker way if you know how to change the exponential to polynomial. Remember, e to the power x equal 1 plus x squared over 2 and plus x cubed over 3 and so on. And then if you have e to the power x minus 1, so I have -1 on the left. So -1, and then this one is gone, right? This one is gone. And then if I divide x, and then I use this to divide x, you will have 1 plus x over 1/2 plus x cubed over, not x cubed, x squared. Over 3 factorial plus x3 over 4 factorial and so on. And you can see that if I subtract 1 and then divide x, I will get 1 plus another polynomial. And when I send x to 0, I will have 1 as a constant, and then the rest of the terms all equal to 0. Then I have reason to guess that this limit is equal to 1. Okay, now how to figure this out? You have to use this weird, the technical term is actually called the Taylor series of the exponential of x. E to the power x, change e to the power x to a polynomial. Okay, and then you figure out that. And for the exercise, you don't have to always do that. Of course, you can put this, you can replace e to the power 2x with another polynomial, but that's too much. That's too much work. So what you do is you memorize this special limit. This special limit is equal to 1. And then you figure out something yourself. I'll show you how to. I'll show you how to. Now, for example 14, you take this limit, and then you will say, oh, this limit is equal to e to the power 2x minus 1 divided by 2x and times 2. Okay, and then you take out 2, and then you have this special limit. But this time it's 2x tends to 0. And this special limit is equal to 1. So you get 2 times 1, that's equal to 2. You see? I kind of used e to the power x minus 1 divided by x is equal to 1. But now my x is not x, my x is 2x. So you don't have to do the polynomial again. If you want, you can. If you really want, you can. But it's not necessary. Okay. B as well, not B. Now, how do I figure out this limit? I will take out a factor, e to the power x, e to the power 4x. And then I will have e to the power 3x minus 1 and divided by x. Okay. In my next step, I will do limit x 0 e to the power 4x, and then this time I will have e to the power 3x minus 1, and then I will have 3x. And then I will multiply 3 here. Okay? And then I will have 3 in front, and then I have 2 separate limits. This one is e to the power 4x, and this one is a special limit. E to the power 3x minus 1 divided by 3x. Now here I can change x tends to 0 to 3x tends to 0, and that will fit more. It will fit my special limit e to the power x minus 1 divided by x. And then I will have 2 limits separately at the same time. At the same time, you see, I don't figure out one and then figure out the other one. I figure out all of them at the same time. It's 3 times. This one is continuous, so e to the power 4 times 0. And then this one is special limit 1. In the end, I have 3. Oh, not 3. Oh, yes, 3. Because in the middle, this is e to the power 0. That's 1. That's 1. Is it fine? So today, I guess the technique part is very similar to the other special limit assign x over x. You still have to create something on your own. The factorizing part is only for the teacher. It's for me. I will factorize this for you using the polynomial approximation of e to the power x as a polynomial, and then figure out for you. And then for the rest, you will try to create something on your own and figure out, use the special limit and find out the limit. Now you can do the exercise. And when you're done, please let me know. Turn on your cameras, please. Okay. Now you can look at my answer. For the first one, I want you to know that x can be negative. That's still fine. Now it's negative x and then minus 1 divided by negative x. And then you can take out negative 1 and then use the special limit. If you are not sure, now you know. You can use negative x. You can. Okay, as long as negative x tends to 0, then it's okay. The key is that it has to be e to the power something minus 1 divided by something, and that something has to tends to 0. Okay. The second one, it has a fractional index, but I hope you're fine with the fractional index because this is what I do. You see, I have a fraction x over 3. I take out x over 3. And I have another fraction x over 6. You have to get past that. It's fine to have a fraction. Okay. And then I will use the special limit here. You can see the special limit. This one. In order to create that, I will divide x by 6. And when I do that, I'll multiply 6. And when I say multiply, I mean divide, because I'm saying that in the sense of in the denominator, I'm dividing. So I'm multiplying the denominator by 6. Okay. And then I will take out 1 over 6. I will send limit to every part of the function at the same time. And then I can take limit at the same time equal 1 over 6. This is not easy. Not easy. You can put down your hands now. Moving on. And the next one is the one that I say, oh, do you remember the previous, after the definition of E, I gave a few, like a variation of this, of a similar expression, but it's not exactly the same, meaning I maybe change the sign, maybe change the coefficient and changed a little bit. And is the limit still equal to E? And that is still, I think, open for discussion. I'll give you a few examples and then you can figure out those yourself. Okay. Right now, we only know that the definition, if you don't remember now, I'll write it again. That is the definition. This is E. No, not this one. Sorry. It's this one. This is E. Sorry, I made a mistake. The other one I wrote is not E. I wrote that was a mistake. Okay. We know this is E. That's the definition of E. We also know another one which is slightly different, which is 1 plus t, but 1 over t like this. T tends to infinity. This is also E. Not infinity. This one is 0. Wow. This one is also E. Okay, the other one I wrote, I don't know if it's E. I don't know, actually. I don't know. Because I wrote this one. I wrote the first, I made a mistake. I said, oh, this is E. I don't know if this is E. I have no idea. I'm kidding myself. I said, this is E. I don't know if this is E, okay? I don't know. If I change the little bit, you see, I change n to 1 over n, I will change the power to 1 over n to n to 1 over n. Maybe this not E anymore. I need to be careful. I need to be careful. One way to be careful, one way to figure out is that you can always use the calculator and input a very large number to actually find out if it's close to 2.718. Then maybe it's E. If it's not, then maybe it's not E. You know what I mean? Anyway, this method you don't have to use the calculator. In this example, you don't have to use the calculator. This is what you do. It's similar like the proof. Remember the proof? Now take this limit, and then you will change it a little bit by little bit. to the until you get the way you want it. This one is 2x, and then you change this to 2x, and then you change it to 1/2, and then you will write the limit 1 plus 1/2x to the power 2x to the power 1/2. And then this is 2x tends to infinity. You know what I mean? Now, in the first row, I write the limit of something of a power. And then in the second row, I might write the power of limit. Okay? And then you know this one is equal to e. This one, it actually line up because this can be n, and this can be n, and this is n. So this is e to the power 1/2. And your answer is e to the power 1/2 is root e, basically. Okay. This one, you see, I changed the sign a little bit. Is it still equal to e? We don't know. We don't know. You shouldn't answer. You shouldn't answer too fast. Maybe it's not e. We figure out. So this is equal to positive. Okay. This is not easy though. How do I know this one? This is not easy, girls. I must tell you, this is not easy. I'm afraid that if I use this method, you may find something wrong. You see, I changed the sign. If the sign is plus, then it's equal to e for sure, right? If this is minus, is it still equal to e? It really is. Now, but I hope that in the future, you can just say this is equal to e. If I figure out this is equal to e, I hope that in the future, you can just use it. But I don't think it's equal to e though. Are you ready? This is not easy though. It's very now to figure out this one, I don't think it's as easy because the sign is changed. The sign is changed. Now, in order to figure out this one, I must go back to the notes, please. Please go back to the notes. Let's go back to this one. Let's go to this one. On page 14, okay? On page 14. Let's figure out this one before we, is it the same? This one is the same, right? This one is the same as the question, isn't it? Yes, this one is the same. So I guess it is difficult then. Can I do this one? Let's go back to 14. Let's figure out this one first. We already know this is the question. This is the same as the example something, right? Let's figure out this one first. If we figure out this one, maybe we can be better. But it's not easy though. I don't know. Let's just figure out using the most ridiculous method. Okay, let's do it. Let's do it. Now remember what you can use is these two, number 1 or number 2, these two. Otherwise, I don't know anyone else is also equal to E, or you are not sure, unless you are sure they're equal to E. But I'm trying to use one of these two. Okay. And this is what I do. This is equal to 1. I will write it as x minus 1 divided by x to the power x. And then I will, this is all because I pretend I don't know what the answer is, but I will, you will see what I do. And then I will write it as x divided by x minus 1. Is it fine? You will not understand why I do that, but I will show you. This is 1 over, this will be 1 plus 1 over x minus 1. Follow me. Is that okay? Now, you know what I did? What I did a lot of things, okay? And then I did, now you would not believe it. I will do this. This is 1 plus x, x minus 1, and then x minus 1, and then multiply this again. Now here I did minus 1 plus 1, you see? Now here I minus 1, but then I multiply 1. So that will make x again. Does that make sense? I hope this makes sense. Okay, next one. This is equal to 1 over limit x tends to infinity 1 plus x minus 1 to the power x minus 1, and another infinity, which is 1 plus limit x tends to infinity 1 over x minus 1. I don't have to write this one again now. Okay. And then it's equal to 1 over e times, this is 1 plus 0, and then equal 1 over e. I know, I know. It looks ridiculous. Because I want, the reason I think that I want this to be I want this to be addition instead of subtraction. This is subtraction, you see. But after I do this, I will make it to addition. And I make it to addition, and then I can use the limit. Okay, but you are not expected to do that though. I don't think that's fair. I don't think that's fair. Anyway, in order to make the your exercise much easier, let me see a question. Sophia, I'm answering your question right now. I'm answering your question right now. Now, you I mean, if you are expected to do this, obviously it's very hard and then it takes too much time and it's not necessary. Okay. So I am, in order to make this easier for you, okay, in order to make all these exercises easier for you, you must use this one and this one, number 1 and number 2, plus something more. So let's go back to the page 14. So on page 14, when I put this down, I say, oh, can you use the negative infinity or whatever? I think you can use this one is equal to E. Okay. Now I give you without proof. Okay. If you don't believe me, you can use your calculator and put n equal to -1,000,000 to check. But in my mind, I think this is equal to E. Now, if you don't believe me, because the whole chapter is based on guessing. So if you don't believe me, you can put in n equal 1 plus, this is -10 to the power 6, and then to the power -10 to the power 6. You can input and see if it's equal to 2.7 or something. Let me try it for you. So in the bracket, it's 1 minus 1 divided by 1,000,000. Okay. And then to the power -1,000,000. Close bracket. Focus, please. You see, it really is equal to. So I think in order to make all your exercise easier, because sometimes you have the negative sign there and then it's difficult if you don't have this limit with you. So you memorize 4.8a, this one. You also memorize this one, and then you memorize this one. This one. Okay, you memorize this is also equal to E. When n tends to -infinity, it also tends to E. And then I think this example can be easy. Okay, Sophia, I think this is your question. I think. Now, I know this look ridiculous, my method, but I encourage you to understand every step I did. Anyway, this looks ridiculous, but if we are allowed to use another limit, which is this one, n tends to -infinity, 1 plus 1 over n to the power n is also equal to E. Now this question can be simpler because you can say this limit x tends to positive infinity, 1 minus 1 over x to the power x is equal to x tends to positive infinity, 1 plus 1 over -x. You just do that. And then this is x, you change to -x, but then you put the -1 outside like that. And then you will say, oh, this is equal to limit -x tends to -infinity, and then this is 1 plus 1 over -x, close bracket, -1. And then inside the bracket, you have E, and then to the power -1, and then you have 1 over E. I think that's allowed. Is that okay? So not just this one, not just this one. This one, I don't know. I still don't know this one. I still don't know this one, but you can figure out yourself using calculator. This one is equal to E. This one is equal to E. Also, this one is equal to E. So that part B is simple. Now you try. You try, okay? I think part B, this part, you also have to use the same thing. You try and you tell me your answer. You raise your hand when you're done. Now, girls, if you have any question, you want to show me your thing, your work, you WhatsApp me, okay? You WhatsApp me. Okay. Now, girls, this one I think it's harder. So I will teach again using the classwork to teach you again. Now this one, this limit, it looks like something, a variation of the limit E, but it's not exactly the same. So what you do is you change it a little bit by little bit. For example, I will change this to 1 over x over 2. Okay. I will not write 2 over x. I will write 1 over x over 2. Okay. So they look very similar to 1 plus 1 over n. And also because this is not x over 2, I will make it x over 2. And after I do that, I will put a square. So they're still equal, you know what I mean? Right? Now, I will use the property of limit, where I put the limit inside. And here you don't have to write x, you write x over 2 tends to infinity. You know what I mean? So this is the special limit. Not the special limit, the definition of limit. And that is equal to e squared. Okay? If you don't know how to write, this is how you write it. For the second one. Second one, like I said, you don't have to use the original definition. You can use the third one, which is tends to negative infinity. You have to use that, otherwise it's gonna, it's not okay. Okay, for this one, x tends to positive infinity, but you must have plus, you know what I mean? You must have plus, so you get 1 over negative 3x. And here you have negative 3x. But you will have 1 over negative 3 like that. Okay, so they're still equal. And then you will put the limit inside. And then you have 1 plus 1 over negative x to the power negative 3x. And then negative 1 over 3. Now this one, you see, when x tends to infinity, negative 3x tends to negative infinity. However, this limit we also based on guessing. I have to emphasize that this is not based on any mathematical knowledge. This is really based on guessing. This is still equal to e. So the answer is e to the power negative 1 over 3. Now you can write 1 over e to the power 1 over 3. That's not necessary. In M2, you are allowed to express the final answer in the negative index. That's fine. Any question? Now I will show you more. Show you more. Example 4. Now these are extra examples. You can't even find it in the textbook. But you will find similar exercise in the textbook. You don't have example, but you have exercise. Example 4. This one. 0 and then a limit. Now this one you must use the second limit, which is the t one, which is this one. T tends to 0 and then 1 plus t to the power 1 over t. This one is also equal to e. Now you use this one. But now t is not t, t is 2x, you know what I mean? So this one is equal to limit 2x tends to 0 and then 1 plus 2x, 1 over 2x, and this is equal to e. Okay, I'm using the second one. Okay. Now for this one, it's negative. This is infinity. And this one, I think I'm using the this one is either 1 is positive, but this is not a fraction, right? This one, I don't know which one this one is not even, It's not the first one because inside is not a fraction. Inside is infinity. Oh, this puts me in a bad. I don't even know. I don't even know. This one. What do I do? I need to first figure out which one I'm going to use. Because if I use the first one inside is a fraction. You see? Because this is infinity, right? This one is infinity, but inside is a fraction. But right now inside is a x, it's not a fraction. So it's not so it's I don't even know. Maybe I can do something like like that. Maybe I will do that, but that will be 0 though. You know what I mean? It's not exactly the same now. This one is not the same. I think there might be a problem, girls. Let me look at the classwork. Oh. Now we don't have time. Maybe you just do the first one. Can you do the first one and tell me the answer? I think first one is very easy, right? You do the first one and you tell me the answer. I think I will check the second one because right now I think it doesn't make sense. I don't think the limit exists right now. Right now. Now you do the first one. You do the classwork, the first one, And let me have a look at the second one. Because right now, because it's even undefined. Now, why I think it's undefined? Because you see, if x is 100, then this is 1 minus 100 to the power 2 over 100. That's undefined. The negative value as a base, that's undefined. So I don't know why this is there. Maybe I put the sign wrong. Maybe I put the sign wrong. So I need to check the original question. So why don't you finish the classwork now? The classwork A, because B is the same as the B. And when you are done, you let me know. You need to wake up because this question is quite simple. For part A, the answer is E, okay? The answer is E. You can use the T tends to 0, that one immediately. Now, let's have a recap. Because it's a lot, it's a lot. In the textbook, you are supposed to know where E is coming from and also make use of 4.8a, 4.8b, and according to my experience, you should also maybe note the 4.8c, this one. The limit is equal to E. Now, 3 of them are all used as definitions, definitions of E. And then there is a whole part that is about E function as a rational number. I mean, irrational number. And both, I think in the case of exponential function and the log, the base, you can often see some E sometimes. Now, as to the limit part, in the textbook, you only have 2 examples. That example 13, the easiest one, anyone can figure out, and 14. Okay, it's just 13 and 14. The 14 one, you're supposed to use this special limit. I call not the definition of E, but the special limit of exponential function e to the power x. Now, this one is done by factorizing e to the power x using the approximation of e to the power x as a polynomial. But when you are solving these questions, you don't have to use the polynomial. You just memorize this e to the power e minus 1 divided by x is equal to 1. And then you just figure out sort of, oh, that's the textbook part. The extra part is the variation of the definition of E, that where you change the coefficient a little bit, maybe you change the sign a little bit, and then you figure out something that's close to E, but not exactly E. But there is some problem with the last one. I seriously, I don't know why I think it's undefined, but I will tell you on Monday. Okay? So on Monday, you prepare these notes and we will talk about this one. In the meantime, do the homework. If you have any question, you can stay. Otherwise, you can leave now.